Welcome to Breadboarding. This is video 45 in the Breadboard 8088 BC series, and in this video we're going to be looking at the CGA video controller, looking at the introduction to it and high-level design. So this is the overall plan where we've been building out a basic floppy disk PC, and in the previous videos we actually managed to get the Breadboard PC booting off IDE disk controller and configured with an IDE BIOS. So the next series of videos we're going to be building out a CGA Colour Graphics adapter video controller. So this is an image of the CGA video card. This comes from -0degrees.net, which is a useful resource for a lot of the early PC information. And this shows that it's based on a Motorola 6845 cathode ray tube controller chip. It has a fixed character font ROM. There is 16K of dynamic video RAM, so this is dynamic RAM. There's a composite video output, so this would go to a compatible monitor with a composite video, and it could also be used with an external RF converter to plug into a standard NTSC American TV. And they've also got the TTL CGA video output. So these were digital outputs which required a compatible CGA monitor. I need to say CGA monitors are quite rare these days and I don't have one, so what we're going to be doing here is trying to get a CGA compatible from a software point of view card here, but with VGA output. And you can see down here that in addition to the CRTC, the character ROM and the 8 RAM chips, we've also got 59 TTL logic chips. So this is a full-length card. Later on you would have found that a lot of video cards would have been a half-length card, perhaps only taking up half its width. So the CGA video controller was available with the first PC from about 1981. But unusually the IBM Colour display, so this was known as the 5153, which was compatible with CGA, was only brought out in 1983. So you had to find alternative monitors for the first couple of years if you had an early PC. Now the monitor works with a vertical refresh of 50 or 60 Hertz, and its horizontal drive or horizontal sync frequency is 15.75 kilohertz, and it makes use of the 14.318 megahertz dot clock. Now that is the same dot clock that's used for the PC and PCXT system clock, and in fact when that clock is divided by 3, this is where you get your 4.77 megahertz system clock from for the early PC and PCXTs. So support for CGA and the monochrome display adapter MDA are actually built into the original PC BIOS and the XI8088 BIOS. Later video cards needed to include a video BIOS actually on the card itself. It uses 16K of video RAM and it starts at B8000 for 16K. I believe this whole range up to BFFFF is probably mapped, so this 16K RAM may appear twice in that address range. The monochrome display adapter actually uses slightly lower address range, so from B0000. It is possible to have both the MDA and CGA cards active in the same PC at the same time because they don't conflict from a memory addressing point of view. We'll perhaps have a look at having both the MDA card that we've already built and the CGA card running at the same time. So CGA outputs are a digital red, green, blue and intensity to a CGA compatible monitor. So this has sort of this pin out, so you'll notice it's different from the 15-pin sub-miniature D connector you perhaps would be familiar with for VGA. It also had the television composite output and an NTSC television compatible with an RF modulator added on. So it's capable of 16 colours, and the IBM Colour display, so the 5153, actually had specific hardware adjustment so that dark yellow would appear actually as brown. Now the CGA text mode was not really as good as the MDA or later VGA. It was only based on an 8x8 pixel characters, whereas MDA originally was 9x14, and in fact in the Breadboard PC we've actually used 8-bit wide by 16 lines for the Breadboard PC. So if we just have a look at what these look like. So this is the default CGA font. You'll see that with 640 by 200 lines, so the vertical lines here are actually 2 pixels wide. So these characters are about 7 pixels wide, whereas there are a thin version of this. So the thin one is the same 8x8, but in fact there's only 1 pixel for the vertical line. So you'll see one looks a bit bolder. And I understand that I think the thicker one was needed perhaps for getting things to work on TV and composite monitors. And in fact, the TVs would really require to work in 40 by 25 mode rather than 80 by 25 mode. So then the monochrome display adapter had 9 by 14 pixel fonts, so they looked a bit cleaner and gave a better display. Primarily, I think this was also to be compatible with the IBM terminals, the 3270 terminals, I believe. And then finally, when VGA came along, then the VGA 80 by 25 is in fact 640 by 400 at 70 Hertz. And this is what we used for the monochrome display adapter in the earlier part of the Breadboard PC project. And these are based on 8 wide by 16 lines. So the text modes with these 8 by 8 pixel characters, we've got 40 by 25 black and white, 40 by 25 with 16 colours. Now those were really more for using with TVs and perhaps composite monitors. The 80 by 25 of black and white and 80 by 25 for 16 colour, you really needed to use a CGA digital input monitor. Now the graphics modes, there was a low res mode, 160 by 100 with 16 colours. So I'm not sure that was used a lot. There are a few games that might have used it, but it's fairly low resolution. A medium resolution that had 320 by 200 with 4 colours out of 2 palettes. Now we'll see in a minute those palettes were not very pretty. Games designers managed to make the most out of them. And then the high res 640 by 200 in black and white. I believe that the foreground colour could also be changed as well in the colour register. And if we look at the comparisons of those modes, the Wikipedia article here has a number of images which we can look at. So it goes you to the Wikipedia article, and down the bottom here we can see that these are various images. So these are all 320 by 200 with 4 colours, and then I think there's one here of 16 colours. And then there's slightly different composite artifact colours down the bottom. So you'll see that the different intensities there, that the colour palettes didn't really result in particularly spectacular images. This is the black and white, slightly higher resolution. And then this was the 16 colour, but obviously lower resolution. And then some of the composite ones. And then further down here it also shows some of the other images. So games would be fairly garish, and some of the other colour palettes weren't quite as bad, but probably this is SimCity, and you can see here with the black and white high res mode and the dithering used for the different shades of grey, I think that is the best looking of the various examples there. And then this one here is actually making use, this is like a Pac-Man sort of look-alike, and this is actually using the low-res 16 colour graphics, so the 160 by 100. So CGA was a little limited, however, there is a project, 8088 MPH Demo, and this was, I think, probably around 2015, 2016, I think this was done, and the demo actually stretches the CGA capabilities to its maximum. This is an animated GIF that just shows some of the key screens. So if you see those sort of images that we saw from Wikipedia and then see these sort of screens, then this is what's possible using composite video tricks. The 8088 MPH Demo uses all sorts of tricks such as changing dynamic RAM timing. It's very dependent on exact PCXT timing, doing 6845 CRTC tweaks and changing RAM refresh rates and all sorts of things. So the composite video tricks are able to get 256 colours or even 1024 colours from the 16, and there is a link there which I'll include in the description below which explains exactly how you actually do that. And if you want to see the whole demo, which is about 8.5 minutes, then I'll include the link in the description below. So this is a screenshot from the test pattern used for the monochrome display adapter, and this just shows that with the blinking disabled we've actually got a high intensity background here rather than blinking, and this was produced at 640 pixels across by 400 lines down. Now in fact when we were testing this there was also the possibility of enabling colour on this. So this is the same test pattern just with a single bit in one of the control registers changed to turn off black and white mode and to turn it into colour. So you'll see that in fact the colours down the bottom here, so we've got black, blue, dark green, cyan, red, magenta, this I believe is brown, light grey, dark grey, light blue, light green, light cyan, sort of orange, pink, yellow, and in fact bright white. So the colours here are actually the same as the CGA colours, and when we were going through this particular video, and again I'll include the link for this video in the screen at the top here and also in the description below, and I actually showed how we modified the colours that were produced here to more accurately match the CGA colour palette as opposed to the later EGA and VGA colour palettes. So the key thing really is the text mode for the monochrome display adapter that we've already developed is almost exactly the same as the CGA text mode. So it's probably worthwhile just talking about the VGA video standard, and because it's difficult to get CGA compatible monitors these days, there are adapters that you can get to convert legacy output into VGA compatible, but it's just easier probably to write VGA from the beginning. So VGA was actually introduced around 1987 in the PS2 range. It differs from the earlier video standards in that it has red, green and blue signals, but with analog levels, so continuously variable from 0 to 0.7 volts. So this means it's able to do a very much larger range of colours. There are still TTL levels for the synchronization signals, and it replaced the MDA CGA and EGA monitors. So these monitors all had digital inputs. It had the capability of having 256 colours out of a possible 262,000. So CGA only had the 16 without using the composite video tricks. EGA had 64. And it had a much better font, so either 9x16 or 8x16. And we used the 8 wide by 16 high in the monochrome display adapter. It used the 15-pin subminiature DIN connector, so that's one you'll probably be more familiar with. And there was a lot of information about the timing data at tinyvga.com. And the key thing is, although VGA is normally known as 640 by 480, this is what you would use for graphics at 60 Hz. But however, if you're only having 25 by 80 characters, then you'd generally be using 400 lines at 70 Hz. If you were to use this one, you'd end up with 30 by 80 characters, which was not the standard screen size that was used for most PCs. So if we look at the Breadboard PC monochrome display adapter design and actually look at where some bits can remain the same and where we need to make changes, you can see the bits in green can remain the same. Bits in red, so the dual port video RAM, we used a 4K chip that had address inputs on both sides and data inputs on both sides, so we didn't have any problems with conflicts between the CPU and the video controller accessing the RAM. But unfortunately these chips are difficult to come by, and to get 16K would be really quite expensive. They're about £20 a chip now, and I only have 2 of them. The things in orange are going to require some changes, but fundamentally it's still going to use the same idea from the design, just slight differences configuration. The character generator on will almost be the same, but we'll be using initially the CGA compatible fonts. We'll also be able to have the VGA one in there, and we'll be able to later stages to be able to look at how those differ. Now, one of the key things to recognise here is that the CRTC produces row addresses, so RA0 to RA3, which determines which line of the character is currently being shown. And when we look at the graphics modes, then we'll need to actually consider which of these raster address lines or row address lines we're actually going to use. There may be some changes to some of the clock timing we need to do. We're going to be using the same VGA digital analog converter, so this allows us to define our palette of information, which is then used to output to the VGA display. But the status and control registers and some of these various multiplexers and control logic here are probably going to need to have some modifications, although there's a good chunk of the text mode stuff that probably can remain the same. So we're going to be able to use a good chunk of the original MDA design for basing the CGA video controller, but we're going to then have to add extra support for handling the graphics. And then over here we're going to need to change the memory map, so the video RAM is going to be a slightly different range. The MDA was at B000, and now it's going to go to B8000, and previously the ports were 3B in this range, and now they're going to 3D. So in fact, the changes are fairly minimal. And there's now an extra colour control port as well. So 3D9 is a new colour control port that the CGA adapter has. But as long as these changes are made here, then the existing text mode will probably be pretty close to being CGA compatible. So for our design, we're going to be using the CGA hard-coded ROM-based font, so much like we did before, but we are going to be using the 16K of video RAM, and this is going to be single-ported video RAM, so we are going to have to put a lot more multiplexing and buffering in there. We're going to be using our VGA Video Digital Analog Converter palette chip, so it makes it easier for driving the output to LCD monitors. Now CGA was 640 by 200 lines with 8 by 8 characters at 60 Hz, so this made use of the 14.3 MHz dot clock, 15 kHz horizontal sync. Now that's different from what we're going to be using for VGA, so we'll come to that in a minute. So if we're using 80 columns by 25 rows, that's still going to need 4K of RAM. So in fact, our video RAM here is capable of doing up to 4 pages of text. Now, in order to do 200 rows of graphics, the Motorola 6845 compatible video controller chips is only capable of doing a maximum of about 127 rows. So to do 100 rows, we can't actually generate addresses for that range. So what the original CGA card, it used one of these row address 0 or raster address 0, is used to select between the lower 8K of video RAM and the upper 8K. And what this basically meant is that if you looked at line 0, then it would be in one block of 8K, line 1 would be the higher block, and then it would toggle between the two. Now with 640 by 200 with 2 color, we use the full 16,000 bytes, and with 320 by 200 we have 2 bits for the color. It gives us 4 colors, and again uses 16,000 bytes. What we're going to do to maintain sort of VGA compatibility, but with the sort of resolutions that CGA has, we're going to be using the 640 pixels by 400 lines with the 8 by 8 font at 70 Hz. But in fact, what we're going to do is to double scan the lines by ignoring the RA0 line, and we'll use the RA1 instead. So what this effectively means is when we're looking at the output, then it won't change on the basis of RA0, it'll only change on RA1. So it means that every line will be repeated. So whether it be a character font or whether it would be the graphics data bit going out. And this is going to be using the VGA 25.175 MHz dot clock, which produces a horizontal sync frequency of about 31.5 kHz. Now I've included some links to the background information used here. So the IBM Colour Graphics Adapter Manual is a PDF document. It's available from various sources, but if I just show you the one from -0 degrees. So a lot of the information I'm going to be showing you comes from this manual. So I'll just quickly flick through it. So there's a lot of the register and programming information that diagram will come to. You'll see it's got all the technical details of how to make one which is compatible, all the various registers and programming modes and things like that. Now these timing values, which are the CRTC register values, these will all be different for the Breadboard PC because we're going to be doing VGA output, which is going to be different timings from this. We've already done those changes for MDA in the BIOS, but we're going to have to make similar changes in the XI8088 BIOS for our hybrid CGA VGA timing card. And then more importantly, there are then logic diagrams. So there's about 6 sheets of logic diagrams that give the detailed design of the card. Now we're not going to go through those now, and it's fairly hard going working out what this actually means. But what I have done in the previous series of MDA, I have annotated a lot of this and actually worked out which bits we need, which bits we don't need. So I'll be doing that over the coming weeks, and we'll go through these schematics in some detail as we come to do the different bits of the card. So this is one of the diagrams which was in that manual, and this just sort of shows the sort of block diagram of things. So the 6845, we're going to be using the same one that we used previously, which was an Hitachi version, which is capable of working slightly faster frequencies. So by working at 3.7 megahertz character clock, that means it can work at VGA frequencies, whereas the earlier one wasn't capable. It also has some capabilities of actually putting programmable skew for some of the cursor and display enable outputs. We're not going to bother with the overscan. Overscan colors was for when we were displaying on a cathode ray tube, whereas with an LCD output and the sort of outputs we're dealing with, generally we don't have to worry about that. The timing and control signals we're going to be doing VGA compatible timing. So this is based on a 25 megahertz dot clock, but we're primarily going to be using 640 by 400 at 70 hertz. Now, in simplification, we're not going to include the color composite generator. So there's quite a bit of logic in the output involved in generating the NTSC color compatible chromium signal, which is added into the composite output. So by not including that, then that will simplify it quite a bit, and it'll also mean that the output stages and the text mode side of things is going to be almost identical to the monochrome display adapter that we've already done. So these are some of the outputs from the technical documentation that I'll be referring back to. So you'll see here that the things in green are registers that we've already got, but all we've needed to do is to change the addresses. So they'll be going from B's to D's. The light pens we're not going to bother with, and there is a color select register, which is a new one that we're going to need to add a new latch to handle the color select register. The alphanumeric mode is almost identical to the monochrome display adapter, apart from the underlining is not supported on CGA, EGA and VGA without using graphics. And it also mentions here it has a jumper controlled character fonts available, so the 7 by 5 wide or the 7 by 7. So those were the wide ones and the thin ones that we saw previously. So when we program the character ROM, we'll put both the wide and the narrow ones in there, and probably the VGA ones as well. So we'll be able to actually switch between the various fonts and see what it looks like. So this is a summary of the graphics mode information, so the low, medium, high, the way how the bits in the individual bytes are actually represented in the various graphics modes. Obviously in the high-res graphics mode, each bit is just 1 pixel. And you can also see over here that when we're in the higher memory modes needing 16K, that the even scans work in this range and the odd scans work in this range. And the way how that's handled is the CRTC raster address line is used to switch between the two of them. Now, as we said in the original design, this you use the RA0 line to switch between the two. Because we want to double scan things to take 200 lines up to 400 lines, we're probably using RA1. And then the color select register, there are a couple of items in here to do with the overscan that we're not going to be worrying too much about, but the rest of it will still apply. And one point to make, the mode control register in the original documentation, the labels here are actually shifted up one, so I'll need to modify this to make the labels stick in the right place. But these combinations of things is what the BIOS knows on how to enable the various video modes, and DOS mode command will also enable you to switch between these video modes. And status register, we're not going to bother with the light pen, so there's only going to be 2 bits of information of interest on the status register. Finally, just before we finish here, let's have a look at the current MDA card. So this is the current monochrome display adapter, which, as I said, is currently capable of outputting color as well with the correct configuration. And this is based on 4 breadboards. So we've actually got 1, 2, 3, 4 breadboards. We've got the CRTC controller is underneath here, the dual port RAM, which we're going to have to replace. Then we've got various things like address decoders. I think there's a character latch there. This is our character ROM here. This is the shift register. Over here we have the VGA output. So this is the digital analog converter with our 15-pin subminiature D VGA connector over here. And then there's some more logic around here, the attribute latch and various other supporting chips to handle all of the attribute timing and multiplexing. So I'm not going to dismantle this card. We're going to leave this card as it is. We'll be using on a new card a lot of the design elements of this. The main change is going to be that we're going to need to include suitable multiplexing around the 32K static RAM chip I'm going to be using for the video RAM. Now, for the moment, I'm only going to use 16K of that, but we might have some options in later videos to be able to increase the color depth and do various other things, perhaps if we make use of more of the video RAM. Okay, so I'm going to break the video there, and if you don't want to miss out on future videos, please hit subscribe. If you could hit like, it just makes the videos available to a wide number of people. In the next video, I'm going to start going into the detailed design of this and updating the schematic diagram, and we're going to start laying out the board and start building the CGA video adapter. Thanks for watching.